Well, thank you everyone for coming. So as usual, we have the seminar today. Today we have Doug who is going to speak about his research, and just like quickly. So if you have any questions, you can if it's a good question, you can ask it immediately. But if it turns out to be like a discussion, please keep that for the end. I think I'll be more than happy to receive questions after that. So thank you very much for coming in person. Happy to see so many people. Please.
Okay, thanks to Jose and Florian for setting this up. Today it's our delight to have Dr. Doug Rowland from NASA's Goddard Space Flight Center with us. As I understand, it's a first ever trip to New Hampshire, and so I'm sure it's going to be going back with lots of leaves and other kinds of souvenirs. So Doug got his undergraduate degree from Caltech, and then went on to the University of Minnesota to get his degree in physics, I believe it is, Doug. Yeah. And from there, he went on and did a postdoc at Goddard, and I guess you fell in love with the place because you've been there ever since. I'll have to say, Doug is I'll say it this way. Doug is one of my longest lasting collaborators in the field. Notice I didn't say longest. And so we've been working on a number of projects together. One of the first was rocket investigation out in Kwajalein Atoll, where we had some rockets to launch there, and Doug and I were roommates. And so every night we went to sleep trying to outdo each other to see who could snore the loudest. I'll say the other interesting thing about it was that both of our wives were pregnant with our first children at that point, and also Rob Pfaff, who was the PI of the mission. They were all pregnant due within just a couple of weeks from each other. So it's easy for me to say that was 19 years ago, because my daughter is 19. And presumably your son is 19 in a couple of weeks. So anyway, so Doug and I go way back, and it's just really a great pleasure to have him here to talk about a couple of other collaborations that we've done that Doug led, the Visions and Visions-2 Saudi rocket mission. So Doug, thank you so much for coming. We're very happy to hear what you have to say today.
Thank you so much, Jeremy. Thanks for the Florian for setting it up and everyone for inviting me. As Jim says, I'm just going to set my time. This is my first trip to New Hampshire, and it's kind of shocking because this is when I started the powerhouse for space physics. And knowing so many New Hampshireites doing science in the field, and just never made it up here. So I'm very happy to be here. Jim mentioned most of our collaboration, but I forgot to say that we're all two academic brothers. We both worked as postdocs with Rob Pfaff. Connections I value, so that was very nice. As Jim said, I'm here to talk about some sounding rockets that we did, one in 2013 and one in 2018. They're called the Visions and Visions-2 rockets, very similar. And their goal was to really study ion outflow. And there's a lot of groups here working on ion outflow and energization. And so we're looking at it in the ionosphere in that context, the source region for ion outflow that then populates the magnetosphere. And it's a fascinating topic to me because it's fundamental plasma physics, but also a lot of comparative planetology. You can study how Mars and Venus differ, how Earth might differ from exoplanets. And I find that really is universal province of high value, plus the system scientific. So I'm not alone in this. I have a team, which I'll show you in a second. But this picture, we've got some discussion. This is from the Allison, what I'll talk about. We went to Poker Flat with the first rocket, Poker Flat, Alaska, Visions 2013. And then the Allison, which Eric was mentioning, is in 2018, which is in the fall. These are our teams. This is Poker, and I know that is during the day. We launch at night, but there's actually has sunlight there. So there's somebody you might recognize. There's Jim, and this is our team. Rob Pfaff is a major collaborator on these. Jim Hecht, who's at Aerospace Corporation, and Mike Hollers unfortunately passed away, and a few other colleagues here. And so then this is the team Visions-2 that was in the Allison for it was in the Arctic winters. So it was 9-20%. So we also have great support from the Sounding Rocket Project Office, all the instrument teams. This is just a small fraction of people that go to make one of these rockets. You have engineers, technicians, machinists, you just need everyone to come together and do it. And we produce, when I say we do the rocket, we do the instrument, which many of you are familiar with. rocket instruments. There's a whole other team that does the rocket itself and the batteries and telemetry and the safety and the, just everything. There's a lot of people involved, and it's not just me here. So the thing I'm talking about is ion outflow. There's other topics that are similar to neutral outflow, but on the Earth, the ion outflow is dominant in the heavier species. And so this is an artist rendition from the MAVEN mission. MAVEN was a mission to study atmospheric escape of Mars. And on Mars, we have ion and neutral outflow, and depending on the phenomenon and the time of year and everything else, different processes can be dominant. So what they're showing in this artist conception is you have the sun there, it's emitting light, electromagnetic radiation, but also the solar wind. And the solar wind carries this magnetized plasma, carries this momentum and energy flux that comes and interacts with the atmosphere of the planet, or the magnetic field in the case of the Earth, dumps energy into the atmosphere, and the energy then gets processed through a bunch of steps and energize some of the gas in the atmosphere to high energy above the escape velocity. And then depending on the species, it ends up with escape velocity to achieve to reach large distances from the planet. So happens at all planets. Any planet with an atmosphere has some kind of escape, whether it's thermal escape or non-thermal escape, we'll talk about here. And it's really just a universal problem. How does Earth's atmosphere escape? And what does it mean for life here and elsewhere? There's a lot of thinking about other planets and where we might find life. Mars has a very different history than Earth. It's much smaller. It has a harder time to hold on to its atmosphere. But another difference is it doesn't have a magnetic field. There's sort of a lot of questions about how magnetic fields work. Do they shield the planet? Do they shield the atmosphere from atmospheric escape, or do they funnel the energy kind of like a sail over a larger lens over a larger area and funnel it down into a more focused region where it can energize the gathering effect? So we have a lot of questions about how atmospheric escape works. It depends on the planet, the atmosphere, the sun, everything going on. And we want to study it here so we can understand it in other contexts. The other aspect of it is the system science. In heliophysics, we're about system science. We care about the ionosphere, which is where I'm studying the thermosphere, but also the magnetosphere is critical. And how that magnetosphere plasma and how that magnetosphere population reacts to solar wind forcing, how it is stable or unstable, how the energetic particle populations and radiation belts behave. And so the ionosphere, if you think about it, the dominant populations typically in the magnetosphere are hydrogen and helium ions. And those can come from the sun or from the Earth. During periods of intense energization of the atmosphere, you can get a lot of heavier ions. You can get oxygen, you can get molecular ions like NO+, N2+, O2+. And so that mass difference, if you go from 1 to 8 or 1 to 16, 1 to 32, you get a very different mass loading of field lines that can change stabilization, that can change ULF periods. You have wave particle interactions that depend on the mass, and then you can change the radiation belts in that way. You can regulate magnetic reconnection and so on. There's a lot of things that happen as you dial that mass number up and down in different parts of the magnetosphere. And so knowing when where oxygen and heavier ions are leaving and where they're going in the magnetosphere, that's what high importance to understanding the overall system. Think about different ways atmospheres can escape. The most obvious is thermal escape. You have your population of gas, and there's sort of gravity of a certain size, and then they're all at the same temperature. The lighter ions and neutrals will have higher velocity, and some of them will just be traveling in free escape. That's sort of the table distribution. And as you go to higher and higher masses, they'll have the same temperature, so they're going to have a lower velocity and typically be bound. So it depends a lot on the composition of the atmosphere, very strong on the temperature of the atmosphere, and probably the biggest is the massive planet. So if you look at how that works for planets in our solar system, this is a very nice chart. The escape velocity on the vertical axis, atmospheric temperature on the x-axis, and the different bodies in our solar system. Some have atmospheres and some don't, but they just listed them all here. You can see that Jupiter and Saturn, they even bind hydrogen. So you wouldn't expect to have a lot of thermal escaping hydrogen in those planets. They're just so massive, they can hold on to it. You go to Earth, and hydrogen and helium free escape from Earth, but heavier gases still in the thermal run. And yet, one of the biggest mysteries of the space age, Lockheed and Shelley and these groups back in the 60s and 70s discovered lots and lots of oxygen and the magnetosphere at different times, typically magnetic storm. So it can't come thermally. How does it get there? So just some fascinating things that I think about. The Earth typically loses hundreds of tons more atmosphere every day than you use planes by thermal escape alone. And it happens that that's about the same rate as the meteoritic input. It didn't have to be that way. Other planets it's different, but it's sort of a nice comparison. And then another number for you is that as we get to escape velocity, for oxygen, you need about 10 eV of energy. Thermal energy is typically about 0.1 eV. So you've got to energize these ions from, and I say ions because I'll tell you why, but it's you get energize the ions by 2 orders of magnitude just to get them to escape. And the neat thing is in the magnetosphere, we see them at tens of keV or hundreds of keV. So you have further process. This is just the beginning of the process. As those ions propagate in the magnetosphere, they get wave particle interactions and other acceleration mechanisms that can get them to much higher energy. Why do I say ions? Because the most effective way to energize these particles to high energies is by electromagnetic fields, which of course don't work. So again, you do have neutral escape. It's very active at some planets like Mars. At Earth, neutrals, hydrogen and helium escape freely, but to get oxygen, you need this ions. And to get the energies, very high energies, you need ionized gas. So we're just talking about exoplanets just briefly. This is a great chart that Catherine Garcia Sage at Goddard made. And this is the typical plot you see in Goldilocks zone versus stellar mass. You know, this is sort of, we're here and the Earth is at 1 AU, and that's a Goldilocks zone where liquid water can remain liquid at the Earth's surface. This is sort of the curve where it's not too hot on the surface and not too cold, the Goldilocks zone column. And you can kind of see as you get to smaller and smaller stars, presumably lower and lower luminosity, the planets get closer and closer to the star to have the same temperature. And you might say, okay, great. So planets that are here, like Proxima Centauri b, should be very habitable, at least from the temperature standpoint. Problem is, there's other effects that come on that are not necessarily scaling the same way as the temperature. And stars are very different from each other. Proxima Centauri b orbits a star that has a very high UV flux, for example. And when you take that ultraviolet flux into the atmosphere into effect, the prediction is that it would have boiled off the atmosphere of Proxima Centauri within a period of 1 billion years or so. So that's still TBD, we don't know. We have to go look at that and see if there's, it sort of depends on what you think of the magnetic field of this planet is and some other aspect of its composition. But it's at least possible that this Goldilocks zone is only one dimension of what habitability means. You have golden temperature is important if you want water. You also need the atmosphere to stick around long enough. And so there's probably other dimensions too, which we're not even showing here. Those are at least 2. So now we talk about, instead of thermal escape, the non-thermal escape process. And there's several keys to this. And one is sort of the collisionality of the gas. You know, we think of the magnetosphere typically collisionless. We think of just the plasma kind of collective behavior and not really worry about collisions for the most part. But in the ionosphere and thermosphere, collisions are important and they become more and more important the farther you go. And ultimately the collisions dominate down here where we're breathing here and also the mesosphere. And there's sort of this transition region where we go from collisionless to collisional, right around the exobase. We call the exobase this transition region where the mean free path of the gas is about scale height. It depends on the density and the temperature and so on, but it's typically around 500 kilometers. Once you have a mean free path that's about a scale height, you can propagate, and then the density is even lower, and you can typically propagate long distance. So when you're in that region, escape becomes efficient. You can still escape from lower down, it just takes a lot more energy. And down here, when you dump energy into the gas, it typically gets quenched, it gets diluted into the bulk gas. So you want to really to efficiently get gas to, you want it to be ionized gas, so you can get those electromagnetic fields activating, and you want to have something that can add to the tail of the distribution, and really, instead of having it always be collisionally quenched back to the Maxwell mean. So that's sort of the picture there. Just think about that exobase. I think that's sort of a critical concept to have. It's a multi-step process. There's so many different things that heat the ions and provide either bulk energy or energy to the tail of the distribution. And they range in altitude as you go from sort of the 90, 110 kilometer region up to the very high altitude of the magnetosphere. And they all matter probably. It's depending where you are and what ions you're looking at, when you're looking at them, they're all important. So you think of the simplest ones down here are sort of the frictional heating as you drive current through the plasma. There's resistance down in the E region, and that tends to heat the bulk gas. Again, you got to dump a lot of energy to give any energy to any given ion because it gets rapidly quenched by collisions. But you can get this here, and you can sort of think of that as setting the stage. It kind of expands the scale height a little bit of everything. Some of that energy is also in the F region, and sort of that DC electrostatic coupling can kind of give you more ions at a fixed height relative to the neutral gas. you also get KV electrons coming in here, producing ions, and also heating and ionizing the gas. In the F region, you have fewer collisions. So you're dumping in energy, you're more effective at getting energy to the distribution because the collisions happen less frequently. So there's also dual heating here that can also help set that stage and kind of inflate the atmosphere a little bit. You also get, that's about where you stop 100 EV electrons, hundreds of EV electrons stop in the F region. And so those electrons, soft precipitation, turns out is very efficient at dumping energy into the ion, whereas harder precipitation, again, it sets the stage, but you're going to get fewer outgoing ions per 20 kV electron than you will per 100 EV electron. There's a couple other processes, there are other ones that I didn't show, but the ambipolar field is a case that was recently investigated by a sounding rocket that you guys were involved in. Endurance, we call it the PI, and that's a subtle and hard to measure effect, but it's important because it's another stage setting piece. Just like the ionosphere is sort of inflated by these heating processes, the ambipolar field is when you have the electrons typically at a larger scale height because they're lighter, and they get to higher altitudes. The plasma wants to remain neutral, so it generates an electric field that pulls the ions or up a little bit. And that typically we think is a few tenths of a volt. Again, we're trying to get to 10 volts, so that's already more than the thermal energy typically, but it's not enough to get us out there. But you can add these building blocks together, and together get 10 eV. One of the most critical seems to be the wave particle interactions, different wave modes that interact with these plasmas. We have ELF sort of gyro resonant modes in the tens of hertz. That's sort of the mass, the gyro frequency the ions we're talking about. We have VLF mode, which can also interact with the ions, and we even have ULF modes like alpine waves that can use Ponder motor force to excavate the ions out. And so typically those work in more low collision regimes, because if you think about resonantly or stochastically adding energy to the tail of distribution, and then it just gets quenched by collision, it's not going to be as effective. So these happen further down, but typically they're more effective at higher altitudes. And the magnetosphere, that's probably where most of the energization happens as the particles stream out. They can then further get energized by cyclotron or other means of the magnetosphere. So all of these matter. This is very hard to measure. This is the whole other rocket spec, so I won't talk about this one too much. We measure these, and we measure this at least down lower near the exobase where this is important. So I just want to make one last comparison, and that's sort of really the Parker Solar Probe experiment. There's some of you recall that. The argument for Parker Solar Probe is you want to go to where the solar wind acceleration happens. Once you're out here, the solar wind is sort of baked in. It's going to have its own energy, its own momentum, its own temperature, and that's just going to evolve in some relatively predictable way. But what sets the solar wind flux and the number flux, the mass flux, is down here in this sort of 3 RS to 15 RS kind of region, and Solar Probe is targeting that with their investigation. So they're looking at the Oregon solar wind. If you do similar, this is simulation analysis. If you do simulations of the exobase region, you can see where the mass flux starts to come through the exobase. This is about 500. That's where it really turns on. And by the time you get to 2,000 kilometers, you basically baked in the mass flux. You can further energize the plasma, dump a lot of energy into it, but the number and the particles, they're kind of fixed by the null. And the reason is all the ions are in the ionosphere. The ionosphere is the densest plasma in the Earth environment, and that's where the source is. And these processes also effectively pull it out. So this region sort of between 500 and 2,000 kilometers, sort of the sweet spot. You want to get above the exobase to really see the processes. We learned that some of the processes happen below the exobase even, so that's been very interesting. But this is sort of the analogy of the solar wind acceleration region. The other aspect, I talked about system science and where these ions go. They go to the magnetosphere, and this is very important for the system science there. This is a paper from the image mission from NOSA 2006. And what you have here are two separate measurements of the same two subforms. One geotail is measuring in situ in the tail what the plasma sheet populations look like. And you have two subform onsets here and here. And 30 minutes later or so, 45 minutes later, you get an increase, a local increase in the particle. So that's sort of the travel time to get out to where their geotails look. At the same time, they had the image mission in the early 2000s, and they had low energy neutral atom fission. I'll talk about that in the rest of the talk, the energy neutral atom fission. And they were able to kind of, from a close to Earth vantage point, image over the whole sky where these ENAs were coming from. And they could remotely sense, this is a direct measurement locally, they could remotely sense ions also going in the same region. So this was sort of the genesis of this, was image had this sensor, I'll talk about the ENAs, that could measure low energy neutral atoms and image them and see where they were going. And then we want to compare with in situ measurements in the same way it was done here. So that led me to think, okay, well, if you could sort of monitor the bulk flow and sort of the total amount of flow that's going out to the magnetosphere, could you also image the source region? There's a lot of questions we have about how do the regions of soft and hot electron precipitation, regions of different field line currents, different regions of electron precipitation, how do those compare to where the ions are coming out? On average, we sort of know what the correlations are, but locally, it'd be very interesting to say, okay, this is a region that has a strong velocity shear, there's different models for how the wave particle interactions are generated. So you'd want to really map out where, if you could image it with the camera, where are the ions coming from and how do they compare to auroral images or electric field or particle matter. This is a heroic attempt by Gordon Wilson in 2003 to take image leading data. Image had a very high apogee. It also had a nice perigee that was close to Earth. And image spun, it was something like 2 minutes every spin. And they could, as they swept through the Earth in the perigee, they could kind of see how many ENAs are coming from the Earth, how many are coming from far away. And they're able to map what during a perigee pass. This is the perigee pass that goes basically over one of the poles. This is the southern pole. And you can kind of see the auroral zone, there's some ENAs coming out. But it's a pretty blurry picture. Why is it blurry? This is a synoptic map. This is actually a case study, but they have another synoptic map. They really don't have any passes that happen right after a substorm. You know, there's taking passes when they come, they've got a long period orbit. Substorm hardly ever happens when you're in that few minutes when you're in the perigee pass. So they just didn't have any. They never had a case where they flew over a substorm. They're moving very fast. They're moving very fast in the region. The satellite is spinning very slowly, and their energy stepping is very slow. So they're designed to study very low fluxes of ENAs in the magnetosphere. They're not really designed to study these close-in high fluxes. And so they really smear everything out. Even so, you can still see there are latitudes where you get strong ENA production and latitudes where you don't. And that was very interesting. And we highlighted the region, but what you need is to really dive in here and see in high resolution what's happening and look at the time duration. So this is sort of the picture. You know, these two rockets missions are looking at how Earth's atmosphere is heated by different processes. You've got either bulk heating in the technical sense or energization of the tail of the distribution. You know, the energy comes in either electromagnetic and field line currents and alpha waves, or it comes in particle precipitation that gets processed to this multi-step process that then heats all of it, not just oxygen, but that's the one I care about. Hydrogen, helium, oxygen, nitric oxide, and so on. So the first mission we did was VISIONS-1. This is a mission that was our first attempt, and we published this last year. This is an attempt to study how the image does the region of ion outflow, compare it with images of the aurora, compare it with in situ measurement, and try to understand. So we would, you know, ideally fly through the ion acceleration region, measure locally what's happening with Jim's instruments, field instruments, and then when we're outside of that region, we'd be imaging the aurora and imaging the neutral atom populations to try to see where the ions are coming. And the way the ENA process works, I'll show you more in a second, but essentially you have ions that are tied to a magnetic field line. They're gyrating, they're moving up and down, but they're tied. So there's an ion acceleration region here. You only have in situ measurement. You've got to fly through it to measure those ions. ENA technique, which was developed in the lab for fusion research and so on back in the 50s, was you have all sorts of neutral gas here, and if the charge exchange cross section is high enough, you can then have a more or less momentum energy conserving interaction where the energetic ion runs into a cold neutral, it strips an electron off of the cold neutral, and you end up with a cold ion and energetic neutral with more or less the same momentum energy. The idea is then, you think about this, the region is where the ions are, but it's emitting this sort of stream of neutral atoms in all directions. And the amount of neutral atoms you get depend on the gas density. The neutral gas density, the more neutral gas you have, the more collisions. But if you have too much neutral gas, those collisions happen, generates an ENA, runs into another neutral, and you never see it. So there's sort of a sweet spot where you have high neutral atom production and low quenching. And up here, you produce lots of ions, but you have hardly any neutral gas to generate. So it's sort of a nice way of probing the vertical structure. So with this rocket, we had a single rocket and we had two payloads, a main and a sub payload. They had different attitude control across one of the sort of particle and fields and payload that also has the ENA cameras, the neutral cameras. This is the Jim's instrument, the electrostatic ion electron analyzer, and Rob back with the electric field and magnetic field payload. That one's spinning, it's aligned with the magnetic fields to try to get full pitch angle resolution, try to get the electric and magnetic field components to spin. We had a 3-axis stabilized spacecraft, which is now, if you're spinning your camera, Marcus Hart here has done a lot of work to make that work, and that's very good work. We didn't quite have the budget to do that, and we didn't have expertise in doing that. So we worked with Jim Hecht to build a very nice, sensitive camera, but it really required a stable platform. So we have that platform is 3-axis control. It's got just a gas jets that can kind of sense the rate around 3 axes and try to stabilize it. And we point that at the Aurora. The other one is spinning and moving around up here, and we kind of look at the same region. So that's sort of our experiment. And we launched from Boca Flat, Alaska. These are ground-based Auroral all-sky imagers. There's a radar here also in Boca Flat. And the apogee for this rocket was about 750 kilometers. You can see the whole flight is only about 15 minutes. So I know many of you have done rocket experiments. This is very typical for a higher altitude mission. 700 kilometers, think about the exobase is maybe in this region. So we're sampling the low altitude where the joule heating is happening. We're sampling the exobase and then we're sampling above that. That's sort of the key is to get that vertical sounding.
So sorry, what are the numbers? What are the numbers at different position? Yeah.
These are seconds since launch.
Oh, okay.
So this is 10 minutes after launch.
Oh, okay.
So this is what we launched into. This is a very typical H-shape from substorm onset. We wanted to launch there. We actually want to launch right up there. You're going to give time for the ions to get heated. It takes some time for the sort of the heating process to really, and the travel time of the ions also is finite. When you're talking about 10 eV ion, it can take a long time, 10 kilometers a second. It can take many seconds to get from 300 kilometers to 700 kilometers. We wanted to launch here. So maybe the payload would resolved heroically by the Wallace team. Got it to launch here. And in some ways it's actually better. I'll tell you what we learned from that. But kind of one of those things, the serendipity of if I had just pushed the button, I would have gone there, but we went there and actually turned out for the best. We have the all sky imagers to showing again the same kind of behavior. We have the onset and then we're launching this sort of the early recovery. This is a mapping of Jim Hecht's multi-channel imagery. He's got a 3914 line, which is nitrogen, sort of similar to the 5577 in terms of interpretation. It looks at where the hard precipitation is down lower in the atmosphere. He's got a 6300 line, which is more the soft precipitation, the red line. And then he mapped these as the camera's looking down, sort of slowly moving. He mapped what that would look like and what those brightnesses were in the two wavelengths. And so what you can see is the trajectory of the rocket is blue here. The instantaneous position at that time is the yellow dot of the rocket. And it's almost like a field goal. I'm not a sports guy, but I was like, this is a perfect 3-pointer here. There's a Aurora over here, and we flew between them. Oh, that's terrible. Except it turned out to be good. I'll show you. Terrible for us because we measured the in situ, but good for the people who produced. So this is some really interesting data that Jim put together, and Rob's data is here. So this is sort of the main part of the flight. When we're above 200, above 400 kilometers on the up leg for about 200 seconds, all the instruments are taking data. The electric field is moderate and it has a very intense flow channel here right at the poleward edge of the Aurora. Jim's instrument is showing the Aurora inverted peak population here in a few kilovolts, and then we're kind of trailing into this region where the energy is falling up, and the fluxes are becoming very high. The electrons going down, field line to 0 degree particles. This is the near mirroring ions, the ions that are near 90 degrees, and they have a strong peak up here, and they go to almost the keV in energy. So you have this region where right at the end, you have all this very intense electron flux, soft electron flux that's very efficient at getting the ions accelerated. You have this ion population that's around the mirroring pitch angle. It's not going straight up. So that's very interesting. Then you have the wave populations here, and also the DC electric field. So you can say, okay, is the DC electric field producing joule heating there much stronger here? And it goes in E squared, the joule heating rate. So this is a much stronger heating rate than this here. Is that? Is it the VLF waves? It's the ELF waves in this case that are sort of gyro resonant with the ions. That would suit the heating. the electrons. So we kind of have to look at that and sort of pick this apart and see what's doing what. But my point was that this flight, this is about the only part of accelerated ions that we flew through. And I'll tell you, we covered image of other populations, but this is the ones we measured here. And when you look in more detail, Jim provided this plot, and this shows the different pitch angle groupings. So we go to electrons, you can see the downgoing electrons, some upgoing secondaries, and some mirroring secondaries. And then the ions, these are the downgoing ions, near mirroring angle, and upgoing. So we say, okay, these are upgoing ions, they're gonna outgo, right? They should all be in this picture thing. It turns out they're here for a very interesting reason. And the reason is because they're being energized either near your altitude, so there's nothing upflowing below, they're kind of being near you, or they're energized above you and then reflected off a parallel potential. And that is consistent with the fact that you also see downgoing here, but not up. So kind of an interesting result. It wasn't what I expected, maybe you expected it because you've flown through a bunch of these. But seeing this dominant of this was very interesting. It kind of had pressure cooker interpretation. This was developed by Gorney, and Jim pointed this out from the data when we first saw it. There's a picture where you have the magnetic mirror force where magnetic field lines are converging, and that changes parallel energy into perpendicular energy until it eventually reflects the particle, and that sort of pushes things out. As soon as you get any perpendicular heating, it gets converted to parallel velocity, and that's what the magnetic mirroring. If you're region of wave heating, typically that's wave heating that's generating perpendicular velocity. So you tend to get heating here that's to push you out. We think we're down here, not getting anything going straight up because we're kind of in this soup where the ions can be perpendicularly energized. But we see downgoing ions. And the idea is there's an electric field at high altitude that's pointed down that makes the ions below a certain energy will reflect off that potential barrier and come back down and maybe bounce back and forth between this point and the magnetic mirror point, gaining energy or losing energy randomly. But some fraction will gain a lot of energy as they stochastically pass through wave heating. And then eventually they'll get enough energy, some of them, to exceed the limit potential, and they'll escape out. So it has a lot of, if this is happening commonly, it has a lot of implications for typical energy and flux of the ions that come out. You'd expect to get maybe fewer ions, but higher energy ions out of a situation like this, although maybe it's more efficient. So we have to do, that modeling is still needs to be done in the measurements, but the idea is that the pressure cooker is happening as indicated by our measurements. That would vary. Now, the pressure cooker we observed was only at the location of the rocket, just that one trajectory. And you saw most of the aurora was happening off to the side. So that's the subject of the next thing, what's happening there in that region. There's the same in situ data here again, separated the electric field components, the waves here, and then electrons lying on the top. On the bottom, I've added spin averaged neutral atom imaging. So we have a 4 pi, essentially every spin, we get a 4 pi picture of the sky. We can figure out where the ENAs are coming from. And this is very simple. We just divide this up, average over a spin, which is 2 seconds, and then divide them into upgoing and horizontal ENAs. Again, my intuition was ions were generated near you at a horizontal pitch angle. Charge exchange reaction tends to conserve that momentum. Most of the ions, most of the ENAs you should see should be horizontal. Well, we saw a factor of 4 more outgoing coming from below, and that was very interesting because that told us a lot about what was happening. In fact, it tells you a lot about the pressure cooker. It's implying the pressure cooker. The other thing is that even though we flew through this region of intense ions, I'll show you in a second, most of these ENAs are coming from further southwest. So they're coming from the region we didn't fly through. So here we are with this idea that we're going to image everything, image the critical region, fly through that same region and compare them. No, we flew through a very interesting region and we imaged this region. So yeah. But in a way, it helps us separate things a little bit easier, I think. So why are the ENAs coming from below instead of horizontally? That's very interesting. One picture is like this. You have this very dense atmosphere. Down here, it's so dense and so collisional. Any particles don't travel very far. The meter path could be meters or shorter. Up here, the meter path is very long, and you have an ion that's sort of tied to the field line and generated with horizontal velocity, and then it can generate ENAs that just take off and go up, essentially ballistically for long distances. So if you have a lot of ENAs generated here, this is the side-looking pixel of the rocket, the horizontal pixels, you should see a lot of flux in these channels. Instead, we see the dominant flux coming from below. And that's, again, it was surprising to me at the time, but this seems so surprising for reflection, is that you have this sort of thin layer where the charge exchange probability is very high, but the density is not so high as to quench all the ENA generation. So what you get is initial ENA generated, and it produces secondaries. It runs into more neutrals and converts some of its energy in. So you might have hundreds of EV or KEV ion, and it might go on to produce several ENAs. Some of them travel down, you never see those. Some of them travel up. We did some simulation of that. So again, what it tells you is that the ions are somehow reaching this region of dense atmosphere. The waves could be existing down there, I'll show you that in a second, or you have a pressure cooker that's taking ions generated here and shooting them back down where they interact with this sort of albedo ENA signal. So we did some simulation. I did a lot of things on this chart, but this is essentially the picture I mentioned. This is a simulation of a 400 EV oxygen ion pitch angle of 90 degrees, and this is altitude versus time. So the initial ion is just sitting there. It will eventually move upwards to the magnetic mirror force, but only after a few seconds, it generates an ENA. Just randomly, we have it collide with a neutral gas. And then that ENA takes off and it goes a little bit down and generates another 2 ENAs, because now we have a scattering interaction. So this 400 EV turns into a 400 EV ENA, but right away it generates a 60 EV ENA and a 340. Then it comes down here, another interaction. And eventually it all just gets this massive chain reaction of generating ENAs, but they're immediately stopped by the atmosphere. So at some point this runs out. But even in this case, you can see we have 2 escaping ENAs of lower energy for one initial ENA, one initial ion. Other pieces that are, I think, critical here, this is probably the only one I'm a little focused on. This was the production altitude. Where do the ENAs come from, typically, that escape? So if I look at this one, it's production altitude is here, this one, production altitude is here. And it depends on the pitch angle of the initial ions, the energy, and so on. But for this particular case, you can see they're kind of generating a thin shell. That thin shell is around 375 kilometers for this range of pitch angles. But depending on the pitch angle, it could be higher. So I mentioned I would show how we knew this was from the other region. Now we're looking at the spin average data before, where we just took all the data from the spin and watched it integrated. In this case, we took the subspin data. So now we look at every clock angle, we know where the rocket is pointing, where the detector is pointing, and then you sweep out a spin, we can see the flux rate as we sweep out different geographic directions. So these are 4 different times in the thing. I'll show you where they are contextually in a second. But essentially we have 3 rings here, a red ring, a green ring, and a blue ring. These are at fixed energy, 50 EV in this case. The blue is the upgoing direction, green is sideways, and red is coming down the field line. There shouldn't be many ENAs produced above you because the collision frequency, the charge exchange rate is so low. This is sort of our noise, the idea is sort of our noise level, our sensitivity level. You can see we have a little excess of horizontal ones coming from the southwest. We have a very large excess of upwind from the southwest. And as you go through the flight, the rocket is moving very far between these different pictures. That directionality is more or less consistent, I'll show you that. And at the end of the flight, the interesting thing is the upgoing becomes very small when we're at lower altitude. This is 448 kilometers, 272, and the horizontal comes down. And again, that's because at some point, you're not getting any ENAs that are generated below you just sequential, so they'll beat it back up. So sort of consistent arrival direction. And when you plot on top of this images from Jim Hecht, this is the more or less stable feature in 6300 just there the whole flight. And so I just took one image representative of the whole flight, but here's 4 different times in the flight. And you can see when the rocket is here, it's pointing back here, it's pointing back here. So we know, and the region where we reached that very intense narrow region line outflow is here. None of the arrows point to the spot. You know, it's just so you know, even back here when we're south of that thing, you expect the arrow to point northward. It's not. So it's pointing back here. So this is a very large region. By contrast, this is a thing fluid. It's very faint, the world image emission, and so presumably much less flux of ions. So that's where we sort of kind of image that outflow this mission. And when you compare it a little more quantitatively, here's another depiction of the same kind of thing. Polar plot of what direction the ENAs are coming from. On the left is the 3914 showing high energy electrons. On the right is the same image, 6300. And so you can kind of see there's 2 intense bands of 3914, and some ENAs come from this band and some ENAs come from that band. So you could say maybe there's some correlation, but this band is more intense. And yet over here, that's also where the 6300 is. So this is sort of another indirect indication of the soft electrons, which is this red emission higher altitude. The soft electrons are really setting this ENA flux with some contribution from the lower energy. I showed that plot of from the image spacecraft of how an image was at the perigee pass trying to map out this region. And this would be about 1 pixel in their image. You can see, even with that 1 pixel, the image was not even resolved, even among multiple pixels. So we have a much better situation because we're moving much slower, the rocket moves slower, we're spinning more slowly, we're stepping faster, we're higher signal, etc. A lot of advantages, and we can image that. And that's sort of where we see the most intense fluxes. Now, we still have a lot of modeling to do because there's a big bias in this data. The brightest images come from directly below the rocket. That's a geometric effect. If you think about ENAs generated with a long slant distance to you, they're more likely to be intercepted and scattered out of the path. The ones that are coming straight up have the least attenuation in the atmosphere. So we've still some modeling. Robert Halperon at UCLA is doing this modeling, trying to get that code working. It's been a very, very long process, but very successful so far. And we're just trying to then invert this and say, okay, now we have this. How do we correct that for that geometry effect and try to see a little bit more structure in that? But it's very interesting. We can see that sort of localized region. The actual production region is probably larger. We're just not done with it because of geometry. So these are the 3 pictures. We know the dense atmosphere is here. These are the ions. We have a wave feeding region that's red. It either extends to some region above the dense atmosphere or it extends down into it. Those are our 2 choices. And then we either have a reflecting potential above the rocket or not. This is with the reflection potential, this is without. So in this case, the ions never interact with the dense neutral atmosphere. They're always generated up here. They generate horizontal ENAs and everything's great, they escape. Here, you get most of your ENAs escaping out the side, and they're just fine. But you get some population where you're heating ions low enough altitude where they generate collisional ENAs, charge exchange ENAs, and then some of those scatter and give you upward going ENA. The third potential, which could be combined with this, I guess, same kind of thing, is that you have ions generated up here, but then the potential shoots them back down to the atmosphere and generate this ENA. So we know some combination of this, and this is happening because we see these strong ambiguity ENAs. So either low altitude wave heating. I'll try to the VISIONS-2 rocket in a second. We see some low altitude wave heating there. Here we have separate evidence from the particle measurement that there's also an parallel. So the real answer is they're probably both happening. Probably we don't have the particle measurement in the same region we're imaging, so it's hard to say for sure. We did some Monte Carlo simulation of this, and just to show that there's this geometric effects and so on. This is just a rough simulation trying to kind of figure out where that image of region of the auroral emission was, put in certain regions, and this is what we got out. We got a region where the energy, where the outgoing edge is stronger than the horizontal, and at the end of the flight, you're seeing more edge on, and that's where you see still more horizontal fluxes. It's not quite matched to this, but the ratio here is about the same as the ratio there. The structure is generally the same. Here, I think in the simulation, we flew much closer to the source than we did in this case. So that's why I feel so much fun to do that. We'll do some more of that analysis. I have a few more minutes. I'm just going to quickly go through the VISIONS-2 because it was going to be different. On VISIONS-2, we also had the DNA imager, but it was, as we pointed out, Neolson is the one place where you can launch in darkness, but be on the day side of the Earth where you're magnetically connected to the solar wind on the day side. Even though it is darkness on the ground, as soon as you get to altitude, you're in sunlight. So the instrument was designed to reject ultraviolet contamination, but it didn't. So it's got a very strong ultraviolet. So we don't actually have ENA images from the second flight. We have excellent in situ measurements, which are actually quite illuminated. So the idea was the same thing at the cusp. The cusp has this very largest observed outflow number of flux on average, and it's got very soft electron precipitation and highly structured electrodynamics. As we mentioned, this is Neolson where we launched, and this is the one long, permanently inhabited region where the cusp goes either overhead or just near overhead every single day. And so during the polar night, you look up from the ground and start and see the aurora. If you're launching a rocket, and there's a radar there. It's just a great spot. And so we were here in Neolson. That's where the facilities, launch range. There's a nice, the radars along your bend. There's a lot of other facilities there. It's just a great, I recommend that you guys get a chance to go. We had 2 rockets in this case for various reasons, mostly because the launches were smaller in Neolson. But it actually worked to our benefit. I'll show you why. So we had one rocket with just essentially the camera, just like before, so before we were on the same rocket. One rocket with just the camera, that's the high flyer, goes by and hangs out and images. Then we had the low flyer, very similar payload to before. We have the the ENA imager, but mostly the particle detectors and the fields. And if we want them 2 minutes apart, but they're meant to kind of be correlated and follow the same track. And we launched into this is a whole other story by itself. We launched into VZ South period. It was very short. We had some really excellent help from our radar facility, the Norwegians there. They really knew how to interpret the ice cap data, how to interpret all the different pieces, and they gave us very good advice. And this happened, and then 45 minutes later, an hour later, that solar wind propagates to where we are, and sure enough, that was a good launch condition as known by the radar. I just want to show off the next made it's so good. We had a similar measurements on VISIONS-1. I just didn't show you the movie, but this is the 6300 channel time since launch. What you saw was the payload separating and the spin happening. Now you're looking at 6300 nanometer emission, and the rocket is flying up over it, then looking backwards, and we're looking back north through the cusp. So you get a lot of cool stuff that he's doing with the altitude profile and the airflow emissions, trying to understand the precipitation. It's actually quite beautiful. And if you look at the other movie, this is the ground-based pulse you're showing, in this case, the 5577 behavior. And you'll see a little yellow dot, which is the rocket coming along there. I'm running a little bit over, but hopefully we do that. So you can kind of see very structured, very time variable, very spatially variable. That's very typical for the cosmos. Okay, so what are the results? We didn't have the ENAs for this, but we saw some really interesting stuff. In fact, we had 2 payloads at 2 different altitudes. It was really fascinating. And so we did observe atmospheric escape. Again, we saw with Jim's instruments some very nice populations of accelerated ions. And there we saw outgoing ions. So it's a little different than the other scenario, because the cosmos was generating outgoing ions where the altitudes where we were. We measured the energy inputs, the waves, and the DC field, and the electrons. And we have new information about the waves that I think is very interesting. This is just an overview of the flight. This is Jim's data. Again, we have electrons, very patchy, not like the inverted V that we saw before, very structured, highly structured. And then we have ions. And so this is downgoing ions, transversely accelerated ions. And these are the outgoing ions, which we had none of in the other picture. Okay, but here we have ions, and what the escape velocity energy is about here. So you're getting some that are even above escape velocity, even at these lower altitudes. So that was very interesting. This is sort of the key that I want to focus on. We also have particles being energized above and being reflected off of a potential or otherwise coming back down. Also interesting were the fields from this rocket. The first rocket also had very interesting fields. These were very interesting to the standpoint of the wave from ULF, the outgoing waves to ELF and VLF. And so Rob Back measured this. We have kind of strong and structured electric fields, a lot of alpine fluctuation with the 2 rockets. And this is just for one of the 2 rockets. Let me just show you. So we have, again, another situation. DC electric fields can be heating, ponder motive acceleration with alpine waves, resonant acceleration from higher frequency waves, and then energization of the electron string. Very complicated. As Jim dives into the data, you can kind of see some really interesting pitch angle energy plots here that show different cases of transversely accelerated ions right at 90-degree pitch angle, low energy. You have lifted tonics, which have just a different behavior in energy pitch angle space. Here's another event that happened at around 290, and you kind of see some of these low energy guys that are getting accelerated down here. So what did we learn? We saw these lifted tonics up to 20 eV of energy as low as 372 kilometers. That's way below the exobase. And so, we're trying to figure out what that is. One option is maybe the solar cycle. The atmosphere was a little bit inflated this time. So our exobase isn't quite what we think it was. We don't actually measure the neutral gas. We should have flown an IG. I'm sorry. That would help a lot, actually. But I want to point out that Chen on the EPOP mission has observed TAIs with their instrument down to 350 kilometers. So these are very surprisingly low. We didn't expect that. We expected them to be 500, 600 kind of energization. Again, because the collisions should be quenching those populations. When we look at it, one of the pieces, the Albanic fluctuation. So Rob made this plot where we have the 2 different rockets, the high flyer and the low flyer. This is the 800 kilometers, it's about 600 kilometers in the middle here. And you can see these very strong Albanian waves that are a couple hundred millivolts per meter, and they kind of continuously extending over this region about 3 degrees in geographic latitude. And they're right on commensurate with the time we see line. But again, there's other waves that are at the same time, electrons at the same time, but at one point on these alpine waves are also very well correlated. There's some great studies. Miller looked at positive motive acceleration of ions by inertial alpine waves, and they showed sort of net negative accelerations in this region. So you have gravity be overpowering your positive motive force, but we see much larger gradient in the alpine wave amplitude, and that would apply a stronger upward force. So we haven't done this analysis again, but I'm very interested in seeing if we have enough positive motive force to overcome gravity, unlike this particular case we're showing. Last couple plots here. So one of the nice things about having those two rockets, we could measure the alpinic power, the amplitude of the two different altitude, and see that gradient, which is due to basically the positive motive force is turning alpinic energy into particle energy. So that's sort of the idea. Here we have the resonant interactions, the ELF and VLF, and we have these are the two cases. This is the high flyer, and this is the low flyer. Here's the upgoing ions and the downgoing electrons, just for context. And what you can see is when you look at the high flyer and the low flyer, the ELF waves here are much, much higher than they are here. The VLF waves are more or less the same intensity. So that almost kind of tells me that the ELF, this additional ELF wave power, it might be doing something, but it's not generating these, because these are the low flyer. So you don't need this to generate these. If you only had this rocket and you had these measurements, you have these ions here, and you would say, I don't know if that's the contribution or not. You can kind of tell because they're most intense here and these kind of stuff. But they're having the two different measurements almost on the same field line, which luckily enough we had the rockets going together, seeing the different altitude profile of these waves. It's something we don't have. We don't have a lot. We just get statistical data from TE1, TE2 that can show wave amplitudes, functional altitude, but in the same event on the same field line with the same precipitation. This is one of the few measurements I'm aware of. I think maybe by Arco or something like that. So it's not very many in the trice. There's a couple of missions like that. So having these different measurements is going to help us model this and put in these different wave populations, different altitudes, put in the alpine population, and see what we get. And it turns out to be very important. Roger Varney did some analysis, depending on where you put the minimum altitude for the wave particle interaction can dramatically change the out plus outflow by a factor of 3. So what altitude you cut this wave particle off is where you really controls the mass flux flow. So a little bit over what I called it, but my conclusions, we do see these low altitude transverse accelerated ions, and they're happening even at 375 kilometers. We see strong gradients of alpinic wave amplitude. The altitude can provide positive motive acceleration, and we see very big differences in the ELF waves, and to some extent the VLF at 2 altitudes. So that could be another modeling study where we go and look at that. So we really need to study altitude dependence of these generation mechanisms and do some more models to see different roles for the different steps, DC, alpine, ELF, and VLF. And then understand this last question. What is the mechanism that drives low altitude acceleration? Is it just the rapid collision rate, or is it just really intense accelerations happening and motive being quenched, or we still see some coming out in the equation? That's all I've got. Thank you for your time. I appreciate it.
This might just be a question about the nomenclature, but could you explain the distinction between the ponderer motive acceleration versus stochastic, please?
Okay, so ponderer motive is a nonlinear mechanism where you have, I'm not supposed to spread some big different, but essentially you have a gradient in the electric field amplitude and accelerate can essentially excavate out particles. They tend to go opposite the opposite the gradient. That's right. So I don't have your answer in my head, but it's essentially a nonlinear effect with intense waves with strong heat and a strong gradient heat, and then change the accelerate the part.
Oh, yeah. No worries. I think that covers it.
Yeah. And so you can see this is the resonator kind of behavior, but also this is sort of this gradient overall, and some of that is due to this absorption of electromagnetic energy conversion in the part.
Thanks.
For this the pressure cooker model for energization and ion production and ENA production, what's the downward going electric field? What sets that up?
There are experts in this room, so I hate saying the thing that generates that is is the currents and the electric field. As the electrons themselves are accelerating, the currents are driven, you tend to need a downward electric field, which tends to pull the electrons out until you reflect lines. So I looked over here because you guys know what you do with more like that. But essentially, there's potential structure above it's 1,000 kilometers, a couple thousand kilometers. Even if the auroral acceleration region a little higher, that can give you that downgoing electric field to shoot electrons out and to reflect lines.
So sorry, just a comment to kind of build off of that and just make sure my understanding is correct. Would it also be correct to say that part of what's driving that electric field is the precipitation of the electrons themselves?
Yeah, I think it's a self-consistent, yeah, in a sense, like the electric field and the electron precipitation are tied. Very closely together. Yeah, exactly.
Awesome.
And so one of the questions Steve Mendy always asks is, is this in a downward current region, upward current region? Because you want the upward current regions where the electron precipitation is happening. That's where you get the downward electron field. I forgot to show that picture, so I'll do that.
That's right, and to clarify on that point, the issue is that, you start with a magnetospheric population of electrons that's isotropic, but a lot of that population mirrors on the way down, and you eventually reach a point where you no longer have enough electrons to continue to carry the current, so there needs to be some means of accelerating them.
To get n times b to be enough. You don't have enough n, so you need more b.
Right.
Cool. It's a good way to think about it.
That's a whole study, just how they roll the fast mission and how they roll accelerating. That was a great result. Any other questions?
The pressure cooker, Monte Carlo simulation has shown that these near 90-degree pitch angle ions resulted in generating ENAs at the angles. Did I understand that right?
Are you asking me?
Yeah. It's just the first
So,
very.
yes, so I did not include, so Robert Alberon has been that measurement. I haven't included that actually. So what I did was I have a population of ions that some of them will be mirroring and stuff. So I sort of simulated in a way, but not correctly. I just put a isotropic group of ions there, and some of them happen to be going down, so they happen to be around in my simulation. Robert Alberon is doing it more appropriately, where he actually put the ions turn up and reflect, and he's finished his thesis, but it had big reactions. So my simulation doesn't show that very.
I guess the first thing I should have mentioned leading up to that, I think I mentioned that there's a region where wave interacting region which causes the particles to be rather away from the parallel. That's where you get more particular distribution. And I thought that was like what you input in doing.
Right, yes, that's what I put in. So and actually my simulation, I don't input that. I just put in the population of ions that are energized by some mechanism. I just assume they're energized by ions. But Robert was doing the thing where you actually put in waves of initial population of ions, of potential field, doing all that stuff. So he's just moved to using lasers to do more Robert. But he hasn't finished.
And the one last term, the albedo reflecting region that.
Yeah.
Did I understand this right? So the further you go down, because it's so dense that you don't really, the ENA don't really come to the detectors, but it's just that kind of sweet spot where you know.
The sweet spot where you maybe have a downward going ion and the first ENA is generated and it may also going downward. It's going to the first momentum. But depending on the impacts parameter and things when it collides, it can draw a different angle. It's the scattering off of things a little bit more. Right. The isotropic. It tends to get you change the direction of the neutral scatter. So yeah, exactly. But you have thin regions high enough to have enough neutrals to get collisions and basically giving backflash ENAs, but not so dense that it absorbs all of it.
It's the event horizon for the.
Yeah.
Raise your hand.
No spaghettification. Thank you so much for your question.
When is VISIONS-3?
I would love to do one. In fact, unfortunately, Michael Collier was responsible for the ENA imagery. He passed unexpectedly a couple years ago. So we need someone to build an instrument. But someone who can really go to we had a student working on ultraviolet contamination. And I think it's the kind of thing you guys do all the time. The difference is the ENA flux are so low, the white liquid acceptable ENA flux for your ball electrons is just swamps.
I did want to say one other thing. Doug is with us the rest of the day today. He's with us tomorrow. So anyone who would like to talk to him, he's located at one of the premier employment institutions for people in our field. So he might be a good person.
And we
to
do
talk
lots
to.
of projects for lots of, you guys, a lot of the stuff you guys are doing, we have people that got it here, I don't do it. A lot of collaboration.
Or other discussions, science discussions, sociological discussion, whatever kind of discussions you think that you'd like to talk about with Doug,
I'd be happy to talk.
just come on by and set you up.
So you said, come on by where exactly?
Far away?
Far away.
Thank you.
Thank you everyone for coming today. Next week, we're going to have the graduates space science seminar series. So we'll have two graduate students for the next week. So, and both are going to be in person.